This is Jack Jackson. In this video, we're going to go over Unit 3 review problems and their solutions. Problems were introduced in the last video, and we're going to go over the solutions here. So hopefully you've worked these yourself. If not, you might want to go back to the previous video in this playlist and just work at the problems without looking ahead and check your work against this solution set. So we're looking at the integral from 0 to 20 of f of x, where we're given this particular function here and given by a table, and notice it goes from 2 to 20. We want 3 intervals, and if you do 3 intervals, then delta x is b minus a over n. That's 20 minus 2 over 3 is 18 over 3 is 6. So we're looking at intervals of size 6. So from 2 to 8 is 6, from 8 to 14 is 6, and 14 to 20 is 6. So here's one interval, here's the next interval, and here is the last interval. And notice we're given information about, for any interval, we're given the information about the left, the right, and the midpoint of that interval. Left, right, and midpoint of that interval. Left, right, and midpoint of that interval. Of course, the right of one interval is the left of the next part. So, working out the solutions, it's for the left Riemann sums, we take each interval, go to the left side, find its height, 1.68, plus the next one, do its height, 5.43, and the last interval, go to the left side and do the height of 2.93. We can factor out the common width of 6 and multiply those together. Adding the heights together, we get 10.04. Multiplied by 6, we get 60.24 for our left Riemann sum approximation of the integral. Similarly, if we do right Riemann sums, it's the same thing, but we go to the right side each time to get the heights. We still have a common width of 6, which we multiply that, and we sum up the heights at 5.43, 2.93, and negative 5.85 there. That sums to 2.51 times 6 is 15.06. The trapezoid 3 estimate is found by averaging the left and right 3 estimates. So add those two numbers together, 60.24 plus 15.06 divided by 2, you get 37.65 for the trapezoid estimate. The midpoint estimate is like the left and right estimates, but we use the midpoint. So we use the 3.78, the 6.21, and the negative 1.29. Notice we are using the y values there, not the x's. Add those up to get 8.7. Again, multiply that common width of 6 to get 52.2. Simpsons, usually called Simpsons 6. I usually think of it still as just being 3 intervals. Some people think of that as 6 smaller intervals. But you find that by doing 2 times midpoint 3 plus trapezoid 3 and then divide by 3. So it's a weighted average of midpoint and trapezoid, counting the midpoint twice as much. So that's 2 times 52.2 plus 37.65, then divide by 3, you get 47.35. Of these, the 47.35 is our best estimate. So if we want to find the average value of a function, we integrate that function over the interval, and then we multiply by 1 over the length of the interval. So 1 over 10 minus 2 is 1/8. So don't forget the 1/8 there. And here I just did it on a calculator and got approximately 169,392. The next one we want to approximate using 18 subdivisions, and this time we're going to use a calculator program to do this. The program that I wrote for TI-84 is the program integral. You put in your formula into y1 for your function, which I've done here. Watch the parentheses there, or use a horizontal fraction line. And then we run the program. It asks us for a, b, and n. Well, a is the lower limit, 2, b is the upper limit, 14, and n is how many subintervals or subrectangles we're going to be looking at. So that's 18. And it gives us in order, kind of tells you here, LRTMS, left, right, trapezoid, midpoint. Simpsons, notice the right, that e negative 4 is really times 10 to the negative 4, so it's 0.3 zeros, then the 8. So that's why that one turns out like that. And that gives us, it just runs that program, so that makes that easy. You could, of course, have done it by hand, but this was much easier to do that. If we approximate that using, here I used a TI Inspire. You see that Simpson's rule is quite close, 0.00133, and this rounds off to 9, 0.001338. So it's almost good. It's good to, well, 5 decimal places. Next, we want to look at y equals x to the 6th, which looks like this. We want to look at the integral from 1 to 3, but just 2 right Riemann sum rectangles. So we're looking at now the area underneath this curve and above the x-axis right in here is the actual integral. The right Riemann sum is going to be quite a bit of an overestimate here of that. But we're finding the areas of these 2 rectangles here by going at the right end of the interval. Halfway between 1 and 3 is 2, so we're evaluating the height at 2 and at 3. Delta x, notice, is 1. Okay, so f of 2 is just 2 to the 6, f of 3 is 3 to the 6, that's 64 plus 729. Each of them are just times a width of 1, and so that's 793. We have defined the definite integral in my class with a slightly simplified version here that says delta x is b minus a over n. That makes the widths of all the rectangles the same. And then xk is a plus k delta x. That puts it at the right side of each one. And the integral from a to b of f of x dx is then defined to be the limit as n goes to infinity of the sum from k equals 1 to n at f of x of k delta x. Or you might place that in place of the x of k here, if you'd rather. So that should definitely be memorized. That if you can use your calculator to integrate from 1 to 3 x to the 6 dx, and it's approximately this. So you should know how to run that on your calculator. For problems 5 and 6, we want to set up an exact value of the solution in integral form, but don't try to find exactly, then use the numerical integration capabilities of calculator to approximate the solution. So the population of a certain region is growing at a constant relative rate of 4% per year. Notice that says a relative rate, not a continuous rate or exponential rate. It is an exponential function with a constant rate. Its current population is given there, 861,752 people. So an exponential growth model like that, you have your initial amount, 1 plus the rate, to the t power. Since that is an annual rate, t must be measured in years here. So 1 plus the 4% is 1.04. Every year we're multiplying by 1.04. That will keep what we've got and add 4% to it. We want to find the average of that, average value of that over the next 15 years. If the current is at time 0 is this, so we're just integrating from 0 to 15, that function times 1 over 15 minus 0, or 1/15. We do it here. When I did it over here, I just pulled that out the front over the 15 and integrated, and we get, well, 1,173,215 rounded to the nearest person. Probably when we look at this basis, 1.04 is basically 3 significant digits. We probably are not going to get an answer any more accurate than that. So we probably should round this to 3 significant digits, which is 1,170,000 people. The velocity of a particle moving along the x-axis is described by this particular formula. V of t equals 12 minus 3t cubed. The particle starts at the origin. What do we get here for the net change in position? Well, the net change in position is just the integral of the velocity. So, well, here I changed, let's see, it's got an x, it should say a t there. Okay, and so the integral from 0 to 20 of 12 minus 3t cubed, here I did it on a calculator and got something different than what I wrote here. Let's see. This might be more accurate, I don't know. 119,760. We'll just use the calculator to do it. There we go. So what does that mean? That means it is that many units to the left of, or in the negative direction of where it started. So if it started at the origin, then it's at that x value on that number line at the end of the time period. That's where that's the ending position. Or it means that it was that much left of where it started, and since it started at the origin, that it was its ending position. The total distance traveled is the integral of the absolute value. Here I did in a calculator. So there it is as far as as close as the calculator goes. Now this may be an approximation because this is an approximation technique on the calculator. Although with the cubic it should do a pretty good job. Okay. The net, so what does that mean? That means if you count all the distance it moved in both directions, this is the total amount of traveling it did. Which you notice is a little, let me go ahead and put a comma in here. It's a little more than what it traveled this way, right? So looks like it went forward some, and then back to where it started, and then even further back to the left at the end. This one here is if the net distance it traveled is the absolute value of the integral, and so that is that. So it ended up 119,760 units away from the starting spot. Happens to be in the negative direction, but that's the distance. Distances are positive. And that wraps up the review problem. So hopefully that gives you a quick review of some of the things that we did in this unit.